hope I'm audible. Hello. Hello, am I audible? Hello, am I audible? Okay, I think the video is fine. It's working well. Okay, so this is a test stream most likely, but I hope that anyone who is watching this may get some help from what I'm going to do. So basically, I'm going to start with GOC today, and here. So I started to prepare some notes here, as you can see. So when you're studying general organic chemistry, what we have here is that we're going to study basically different kinds of effects. First of all, we are going to see electronic effects, and based on the electronic effects, we are going to study steric effects that are accompanied by it, the field effects, the application of these effects, acids and bases in organic chemistry. Everything will be based on these electronic effects, most likely they will stem out of it. And finally we'll see aromaticity. Okay, we'll see aromaticity in the end. So aromaticity, however, for me will be a part of both organic chemistry as I'm sorry, not organic chemistry, will be a part of both acid and bases as well as aromaticity in itself. So we'll see that in both the cases. Okay, so firstly talking about inductive effect. Now inductive effect is a kind of effect that involves separation of charges. Now when I talk about say chlorine and carbon, chlorine and carbon are attached to each other, and when they are attached to each other, you can see that carbon, being less electronegative, uh, has to give up the bond pair or the bonded electrons more towards the chlorine side. Since it's a covalent bond, it's not a complete transfer of the electrons to chlorine, but the shared pair of electrons among them moves slightly more towards chlorine since it's more electronegative. However, if the bond is just between carbon and carbon, there won't be any separation of charges. So when there is no separation of charges, there will be no creation of polarity. So if you want to make a bond polar, the electronegativity of the bonded atoms must be different, and otherwise there won't be any separation of charges. So inductive effect stems out of this. Now inductive effect is distance dependent. That means if I say I have a group G, this group G, if it is electronegative, the attached carbon to it will have some delta positive charge, and this delta positive charge will be the highest of all, because the carbon next to it won't have that much of effect on it as compared to the carbon that was just adjacent to the group G. So it will have a smaller delta delta positive charge, and the next one to it will have an even smaller delta 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 positive charge. So this effect, the magnitude of this effect decreases with increasing distance. So this is the most important part of it. And another thing that I would like to talk about is that people often confuse inductive effect with what we call as dipole moment. So they are not same. When I talk about dipole moment and inductive effect, they are not same. Now when you talk about dipole moment, you will notice that in case of dipole moment, any bond that is present will have a positive and a negative charge itself, whereas in inductive effect the adjacent atoms will have the same charge, although in a more diminished manner. So if there is a bond between A and B, there will be a delta positive and there will be a delta negative charge. This is dipole. But if you have some A, B, C and same C, 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 okay, let's just take one. Let's take A. So if some A, and if you have some carbon here, say here there will be say some delta charge. If there is delta negative, it might be reverse as well. There must be delta positive here, then there will be a delta negative. So in any case, there will be same charges, there will be like charges. This is inductive effect. Okay, this is inductive effect. So they are not the same. Now, so let's make a small comparison between them. How do they actually work? If you take a look at this, so in case of dipole moment, in case of dipole moment, what happens is that there is induction through space. Okay, there is induction through space. So induction of charge through space. Whereas if you talk about instead of dipole moment, if you talk about what we call as inductive effect, in inductive effect the induction of charge is through bonds. So just to tell you once again, see, it operates to sigma bond. It operates to sigma bond. So whatever charge is being distributed through this sigma bond itself. This is a sigma bond, and it affects through this. So it moves here from here and like this. Whereas in dipole moment, it operates through space. So here induction of charge is through space, where here the induction of charge is through sigma bond. Okay. um, Secondly, if I talk about dipole induction, there will be dipole induction in this case, means there will be just a positive and a negative pole. There will be dipole induction, and there is no dipole induction here. Dipole induction means just a positive and a negative end. That is called dipole, means two poles. Whereas in inductive effect, we have already seen that there is a possibility of several charges on more than one carbon. So there is no such dipole thing. Then here what happens, polarization takes place. So this is a result of polarization. Whereas in case of inductive effect, there is no such polarization. There is no polarization. So polarization does not occur. So that is why it's called polarization effect. Whereas here you have what we call inductive effect. Okay, I hope it's clear. If anybody has anything to ask, let me just check the comment section for once. If not, then we'll move ahead. Okay. So thus we'll have two types of inductive effect here, if I talk about. So talking about the types of inductive effect. You can either have one case where you will have only and only movement from a carbon towards the group. This is one possibility. On the other hand, the other possibility is that instead towards the group, it will move away from the group. Okay, so in this case, what will happen in the first case, since this is occurring, there will be a delta negative charge here. Here, what will be happening? There will be a delta positive charge. So thus there will be a delta positive over here, delta delta positive, and delta 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 positive over here. Similarly, this will be delta delta negative, and there will be delta negative over here. So when this is occurring when electronegativity of carbon is less than electronegativity of G, and this is occurring when electronegativity of carbon is greater than that of G. Okay, so this is called this is called minus I effect. This is called minus I effect, whereas this is called plus I effect. Okay, so minus I effect is when you have movement of electrons from away from the carbon, and plus I effect is when there is movement towards the carbon. Okay, so now talking about the features of sigma bond. So features of inductive effect. So firstly, it is a permanent effect. It is a permanent effect. So permanent effect are of three types: sigma, inductive effect, mesomeric effect, and hyperconjugation. So it is a permanent effect, and if it operates through sigma bond, we already saw that. So we are already seeing the features of inductive effect. So let's just club them together. Okay. So now let's talk about what we call the difference between temporary and permanent effect. Okay. Difference between permanent and temporary effect. So in permanent effect, there is a permanent delocalization of bond. Okay, whereas in temporary effect, the localization is there. Slightly, sometimes there is a delocalization. So means permanent effect is something that is inherent property. Okay, permanent effect is inherent property of the molecule. Whereas talking a temporary effect, it is not an inherent property of the molecule. So what happens is that in case of temporary effect, the molecule actually acts in presence of some external reagent. Okay. So as soon as the reagent disappears, the effect also disappears. Okay. So temporary effect, we'll see the temporary effects later. So like there will be electromeric effect, for example, we'll see. So temporary effect, it occurs in presence of an external reagent, and it vanishes as soon as the reagent vanishes. Okay, it moves away as soon as the reagent vanishes. Okay, so since we have already talked about plus I and minus I effect, let's talk about how do they act. Okay, so first we'll talk about the plus I groups. Okay, so let's first talk about the plus I groups. Okay, let me use a different color. So plus I groups are of different types. So one type is the alkyl groups. Okay, one type is the alkyl groups. Second type is the negatively charged groups. Okay, second type is the negatively charged groups. So negatively charged groups as well as show plus I effect. Then we have the less electronegative groups, means the ones that are less electronegative than carbon. And then we have the isotopes. The isotopes, that is hydrogen, deuterium, tritium. Okay, so we have this. Okay, so these are uh, the groups that are electron donating in nature. Okay, so plus I group are electron donating in nature. So if you talk about, so let's for example take, so plus I groups are electron donating. So for example, let's talk about what I call NOH group. Okay, this is an alcoholic group, and here if I take an O negative methoxy group, When I talk about this group, this group shows minus I effect. Okay, but it's since this group is negatively charged, it will instead show plus I effect. Okay, because it's electron rich, so it is beneficial for oxygen to donate some of its electrons to the adjacent carbon. Okay, so this shows plus I effect. Okay. So talking about the negatively charged groups in order, negatively charged groups are the best electron donating groups. Okay, negatively charged groups are the best electron donating groups. So negatively charged groups are like CH2 negative, O negative, NH negative, SH negative, CO negative, etc. Okay, these groups are negatively charged, and so they are uh, plus I groups. Okay. Now, if you talk about this group is not directly attached to the carbon chain. Here, the negatively charged is indirectly just inducing a negative charge on the carbon, and the carbon that is present on this carboxylate ion is actually inducing negative charge on itself. So this electron density is pushed towards the carbon. So if I talk about the first tree, okay, if I talk about the first tree, you can already see that here carbon is the least electronegative of all. So if I compare the plus I effect, you can say CH2 negative has the best plus I effect because it is least electronegative of the three, whereas O negative has higher electronegativity, so it is the least plus I inducing of the three. Now the question is that between O negative and S negative, which one will be more? So the answer is that S negative, since it's less electronegative, it will be more plus I inducing as compared to O negative. So let's not talk about all the groups that are less electronegative. Okay. So in less electronegative groups, we have, say, MgBr. This has been formation of Grignard reagent. SiMe3. We have Li, COLi. Okay. So again, if I compare silicon and magnesium, for example, magnesium is more electropositive, so it is higher plus I inducing. Okay, it is higher plus I inducing. Let's next talk about isotopes. Okay, so among isotopes, we know that here the bond strength so if I talk about carbon deuterium, just carbon deuterium and here carbon hydrogen. So this is the order of the bond strength. Okay, it is the order of the bond strength. So strength wise, this is the most. So talking about vibration will be opposite. When the strength is higher, the vibration reduces. So here, this is the order of this. Talking about length, obviously length, this one will be higher since the bond strength is weak. So plus I effect reduces with increasing strength. Increasing distance. So since this happens, what actually will happen is that the plus I effect, since it reduces with increasing distance, so what actually happens is that in this case the distance is higher, so now lengthwise this is higher, so that's why you will have least plus I effect. So hydrogen will be less than deuterium and deuterium will be less than tritium in case of plus I effect. So talking about the alkyl groups, similarly in alkyl groups the primary will have less than secondary, and secondary less than tertiary alkyl groups. So the reason is because the plus effect of carbon is more than that of hydrogen. So replacing the groups, replacing the hydrogen in the groups with carbon will induce higher plus effect. So next we'll see so here if we apply distance, so here we can apply something called dBn rule. Okay, dBn rule. So D stands for distance, B stands for branches, N stands for number of carbons. Okay, so this is dBn rule. So this will help us in understanding the plus I power. Okay, so plus I power, if you talk about, it will decrease with increasing distance. Okay, plus I power is inversely proportional to distance, and it is directly proportional to number of branches. It is directly proportional to the number of branches, and it is also directly proportional to the number of carbons. So let's check with some examples. So let's take for example CH3, CH2, and let's hold it to C. PC means parent chain. Okay, PC means the parent chain. So if I take this group now, so here as you can see, here since I have number wise, this is more, so between 1 and 2, 2 will have greater plus I effect than 1. Okay, 2 will have greater plus I effect than 1, because here number wise carbon is more. Now let's take second example. So say here I have CH3, CH, CH3, CH2, and here I have the parent chain. This is 1. And in second case, if I have CH3, CH2, 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 parent chain. Okay, so here I have 6 carbons, here I have just 4 carbons, but we know that this has a branch over here, this has no branches. So what wins? 1 wins over 2. 1 wins over 2 because here number of branches is 1. So which is why, since according to dbn rule, what will happen, distance is important over b, and b is important over n in terms of priority. Now let's take another example. So now I've taken cs3 ch ch ch2 parent, and here I've taken cs3 ch2 ch ch3 ch2 and a parent chain over here. So as you can see now, the branches are same, but distance wise this is on number 3, distance wise this is on number 3. So that's why what will be, so distance wise this is on 3, and here it is on 2. So in case of 1 and 2, 1 is going to, sorry, 2 is going to win over 1, 2 will win over 1. So again let's reiterate by taking another example. So here I have say cs3c ch3 ch3, here I have cs2 cs2 with the parent chain. Now instead here what I have a ch2, I have a cs3 ch2 in the parent chain. If you take a look at this carbon is present on the second number, whereas there are two that are on third position. So no matter what, here what will win, second will win over first, because distance wise it's closer. 2 will win over 1. 2 will win over 1. Okay, so let's take one final example. Here I have cs3 ch2 cs3 ch3 and a parent chain. Secondly I have a cs3 ch2 ch a ch and cs3 and a parent chain. And thirdly I am taking cs3 ch2 ch2 a cs3 cs3 and a parent chain. If you see here on this carbon I have 2 methyl, that is number of branches is 2 here, Here number of branches is 1, here number of branches is 2. But first see, you'll win by distance. Distance wise, you have 1, here you have 1, here you have 2. So 3 wins overall. 3 wins overall. But between 2 and 1, now what is going to happen? Here you have 1, here you have 2. So 3 over 2 and 2 over 1. That's why this is going to be the order. Sorry. It will be 3, 1 and 2. Okay, 3, 1 and 2, because here you have 2 methyl, here 1 methyl, here you have 1, here as well. This is increasing, so 1 will be ahead of 2. Okay, so let's try another question. So here I have CH3, CH2, CH, CH2, parency. Here I have CH3, CH3, CH2, CH2, CH, CH3 and a parency. Here I have CH3, CH2, CH, CH2, CH3, and here I have CH2 and a parency, and here I have CH3, CH2, CH2, CH, CH2, CH3 and a parency. So now let's talk about this. So here if you see between 1, 2, 3, 4, we can already see that 2 and 4 are winning. 2 and 4 are winning because the methyl groups and alkyl cycle. So the question is that which of the two will win. So we can see here distance, but n is winning here. So 4 will have higher, so 4 will have the highest as compared to 2, okay, and then 3 will have a higher as compared to 1 plus I factor. Okay, so now I'm talking about minor side groups. talking about the minus I groups. So when I'm talking about the minus I groups, we know one thing for sure, that of all the groups that we have seen, just like the most negatively charged groups are the best, or the best in when you talk about the plus side effect. Similarly, the negatively charged ones win over all others. Then in this case, so negatively charged, then more electronegative groups than carbon, then we'll have alkyl, okay. So first let's first compare the comparison. Okay, so comparison wise, so comparing plus I power, so negatively charged wins over less electronegative groups, and less electronegative wins over alkyl, which wins over isotopes, which wins over isotopes. So if we talk about the overall trend, so CH2 negative wins over NH negative for electronegativity reason, which wins over O negative. This wins over C double bond O negative. Then comes the less electronegative groups, where magnesium wins over silicon, and here you have 3 degree alkyl winning over 2 degree, 2 degree over 1 over methyl, and dissolve win over the isotopes. So among the isotopes I have tritium, deuterium, and hydrogen has the least of all power. So I have a good question for you now. I have a good question. So I want to see if you can think about this or not. So take time and think about this question. So say if I have to compare, so I have to compare among CH3, CH2T, CH T2, and if I have to compare between CHD2. So if I have to compare among these four, which one do you think? Obviously, you know CH3 has to be last of all. We already know that CH3 has to be last of all because it does not have higher isotopes. So this one's over on. What about the rest of the three? हाँ जा रहा हूँ नहीं अभी नहीं लिया, अभी नहीं लिया। हम्म? आप अभी जाएंगे? अच्छा आप लेके आएंगे अभी? हाँ ठीक है ठीक है। Okay, so CH2 wins here. Oh, that is sure. But the comparison between CH2T and CHD2 is the most perplexing one. Now, what do you think? Are 2D is going to win or 1T? The answer is that instead of one 1T, we'll have 2Ds winning. Because you have to think from the perspective of hydrogen. Okay, so more it is hydrogen overall the sum wise, because D is more in number, so it wins. Okay, let's next talk about the plus I groups. So, okay, sorry, let's talk about the minus I groups. So in minus I groups we have positively charged groups, then we have more electronegative atoms, than carbon. Okay, then you also have, so these two are majorly present here. Then you have unsaturated unsaturated substituents like carbon carbon double bond, carbon carbon triple bond. They also serve the purpose of pulling the electrons away through sigma bonds. Okay, so these are the major ones that we'll see. Now let's talk about, on the compress, if I took my OH negative, OH versus CM. Okay, OH versus CM. Assuming that minus I strength higher, the answer will be this: C triple bond N will win over OH negative in terms of minus I strength. Why? Because if you talk about the hybridization, it is sp over here, where the hybridization is sp3. So electronegativity of oxygen sp3 will be less than that of carbon sp. Okay, so that is why that's why it's continuing. for anyone who is thinking why sp carbon is more electronegative, I think that you have more s character wins. So suppose you have sp3 carbon. In sp3 carbon you'll have a long bond. Okay, you have a long bond. So ch bond is longer here. In sp2 what happens? This is shorter, this is shorter, and it is more rounded, more rounded. So and in sp case it's even more rounded, so bond distance decreases. Okay, bond distance decreases. This is inversely proportional to s character. So s character increases, so bond distance is directly proportional to s character. Yeah, inversely proportional. So as character increases, bond distance increases, bond distance decreases. So here's something that will apply, that is called one jump rule. Okay, so we'll apply something called one jump rule in terms of hybridization. So when you're talking about hybridization, the hybridization, if it is sp and if it is sp3, there is a jump of sp2 from reaching sp3 to sp. So then what happens is that sp wins over sp3. Okay, so between adjacent elements, if the hybridization is sp and say sp3, then the one that will have sp3 will win. Okay, so observed in, this is observed in case of observed in case of carbon, nitrogen, oxygen, fluorine. So electronegativity increases, but between adjacent carbons, if you see, so if I have say an adjacent carbon over here, increasing of adjacent atoms. So if I have carbon as sp hybridized, it will win over nitrogen, that is sp3 hybridized. But if carbon is sp2 hybridized, then nitrogen of sp3 hybridization will win. Okay, in terms of electronegativity. So this is the most interesting part. So similarly if I talk about carbon, that is sp hybridized, it will lose to oxygen, that is sp3 hybridized. because they are not adjacent. But nitrogen, if it is sp hybridized, it will win over oxygen, that is sp3 hybridized. Okay. Similarly, if nitrogen is sp2 hybridized, it will lose to oxygen, that is sp3 hybridized. This is one jump rule. Okay, this is the one jump rule that we're talking about. Okay, so we'll stop here right now. I'll continue the stream later on.